Oh, hey there. Welcome to Calculus for Dummies. Today, we're diving into the world of ordinary differential equations, or also known as ODEs, and learning about one of the fundamental numerical methods to help solve them, the Euler's method. Now, if you're new to ODEs or just looking for a refresher, you're in the right place. But before we get started, don't forget to hit that subscribe button and ring that notification bell so you won't miss any future tutorials. Now, let's jump into it. Firstly, what is an ordinary differential equation? Well, it's an equation that involves a function and its derivatives. We often encounter them in various scientific and engineering applications like modeling population growth, electrical circuits, or chemical reactions. Now, Euler's method is a numerical technique that allows us to approximate the solution of an ODE, especially when we can't find a closed-form solution. It's a step-by-step approach that's both intuitive and relatively simple to implement. Nevertheless, here's the step-by-step guide on how to use the Euler's method to solve ODEs. Step 1 is to write down your ODE. Let's take a simple example. dy over dx is equal to x plus y. Now, remember that this way of approaching ODEs revolve around conditions. These conditions simply just have to be met in order for the formula to smoothly glide throughout the whole problem. In continuation, move on to step 2. Here is when we choose a step size, and we assign that to the variable h. This determines how far we move along the x-axis in each iteration. Be cautious though, because too large a step size may lead to inaccurate results, while too small of a step size increases computational cost. Then we go to step 3. This is where we initialize. We are going to choose an initial point where you know the solution. This is our starting point. Moving on comes the fun part. Step 4 is iteration. We are going to use the formula y sub n plus 1 is equal to y sub n plus h times f of x sub n and y sub n to find the solution at each step. This step can be repeated until you reach your desired endpoint. During the iteration phase, what we did to solve the problem were as follows. To find x sub 1, we first needed to add x sub 0 to h. With the values, this equals to 0 plus 0.1, which in returns is equal to 0.1. Next is to find y sub 1. We first needed to add y sub 0 plus h times f of x sub 0 and y sub 0. Again, with the values, this equals to 1 plus 0.1 times 0 plus 1. This equals to 1.1. Now, as I've said, this process could be repeated until you reach your desired endpoint or a specific number of steps. So, moving on, we looked for x sub 2 by adding x sub 1 plus h, and with the values, this equals to 0.1 plus 0.1 equaling to 0.2. And moving forward, we looked for y sub 2 equals adding y sub 1 plus h times f of x sub 1 and y sub 1. With the values, this equals to 1.1 plus 0.1 times 0.1 plus 1.1, ultimately equaling to 1.23. And there you have it, folks. Euler's method in action. We covered the basics, the derivation, the summary, and walked through a step-by-step example. Well, I hope this helps demystify solving ODEs using numerical methods. If you have any questions or if there's a specific topic you'd like me to cover in future videos, let me know in the comments below. If you found this video helpful, please do leave a like, subscribe, and ring that notification bell, as it does help me and my channel a lot. Until next time, and happy solving!